Okay, imagine this. Every single second, millions of your emails, your texts, your streaming movies, they're all handed off to routers that are, well, completely blindly lost. Seriously. Welcome to this explainer. Today we're diving into the meat of Chapter 25, focusing on how IPv6 routing actually works. We're going to see how these devices desperately use digital maps to stop your data from just falling into the void.
So what exactly happens when a router receives a data packet, but it doesn't have a matching map for that destination? Like, what does it do? Does it hold onto it? Ask a neighboring router for help? No way. It just completely destroys it, straight into the digital trash. Without a map, a router is basically paralyzed. And, that is exactly why building that map is literally the single most critical function in networking.
Let's jump into Section 1, the router's blind spot. How routers make decisions.
Think of a router as this massive, chaotic intersection, right? You've got packets flying in from all directions. Now, to decide which road a packet should actually take, the router relies entirely on what we call a routing table. When a packet arrives, the router has to de-encapsulate it. That's basically just a fancy way of saying it opens the digital envelope to look at the inner IPv6 destination address. It then compares that address directly to this table. If there's a match, boom, it gets a green light. If not, like we said, straight to the trash.
Moving on to Section 2, Automatic IPv6 Route Mapping, Smart Self-Configuration.
Now you might be thinking to yourself, wait, do I really have to manually type in every single destination in the world? Well, fortunately, no. The really brilliant thing about IPv6 is that the second you turn on an interface, the router actually maps its surroundings automatically. It automatically adds two things. First, a connected route. Think of this as a /64 prefix representing the entire street the router is attached to. And second, a local route. That's a highly specific /128 prefix identifying its exact driveway, or host IP. So it essentially knows its own neighborhood and its own front door, without you lifting a single finger.
All right, Section 3, drawing the map manually, configuring static routes. So that covers the local stuff, but what about remote networks? I mean, how does a router reach a server in another country, or even just the next building over? To bridge that real-world physical gap across those huge bundles of cables and server racks, we, as network engineers, have to draw the map manually. And we do this using what are called static routes. Basically, we are giving the router explicit, typed-out driving directions.
To actually pull this off, we use the IPv6 route command. It's a pretty straightforward three-step process. Step 1, identify the destination prefix, like where are we actually trying to go. Step 2, choose your local outgoing interface. Or Step 3, specify the next hop IPv6 address, which is basically the IP of the neighbor router you're handing the packet to. Seems incredibly simple, right? Well, hold that thought, because here is exactly where things start to get a little messy.
Okay, here is a massive gotcha that catches out almost every beginner, for sure. You know how IPv6 has those link local addresses, right? The ones that usually start with FE80? Now, those are strictly meant for local chatter between neighbors. But if you try to use one of these as your next hop address in a static route, the standard routing rules completely, and I mean completely, fall apart.
The fix here is super strict. Link local addresses absolutely must be paired with a local outgoing interface in your command. See, with a normal global address, the router is smart enough to sort of reverse engineer and deduce which interface to use. But with a link local address, it's totally blind. If you don't explicitly specify the interface, the router can't figure it out, and it will actually just outright reject your command with an error. No way around it.
Let's look at another hidden trap. Because there's always more, right? What if we move away from those simple point-to-point serial cables and use Ethernet instead? On an old-school serial link, it's easy. There's literally only one guy on the other end of the wire. But Ethernet? That's a multi-access network. You could easily have 10 different routers plugged into the exact same switch.
And because of that crowd, on Ethernet connections, you always have to include the next hop IPv6 address. Listen to this. If you only list the outgoing Ethernet interface, the router software will actually accept the command. It looks perfectly fine on the screen, but because it doesn't know exactly which of those 10 routers on the switch to hand the packet to, it just drops the traffic. It's a completely silent, deadly failure that can take hours to troubleshoot.
All right, let's move to Section 4. Spare tires and defaults. Backup plans for your network.
So, what happens if our manual map fails, or a packet arrives with a totally unknown destination? Enter the static default route. I like to think of this as the giant, when in doubt, go this way sign. By using a prefix of /0, which just means all zeros, we give the router a fallback path. Instead of instantly destroying the lost packet, it hands it off to this default route, which usually points straight out to your internet service provider. But here's a thought. What if you have competing maps? Say you have a manual static route, but also a dynamic route learned from a protocol like OSPF. To choose the winner, the router uses something called administrative distance. It's essentially a believability score. Connected routes score a 0, static routes get a 1, and OSPF gets a 110. The golden rule here, lower numbers always win. So by default, your router is always going to trust your static route over OSPF.
But, and this is a really cool trick, we can actually weaponize this scoring system. By manually changing a static route's administrative distance to, say, 130, we intentionally make it worse than the OSPF route of 110. What we've just created is a floating static route. It acts exactly like a spare tire in your trunk. It hides invisibly in the background, and it only floats up into the active routing table to save the day if your primary OSPF route completely fails. How cool is that?
Okay, final stretch. Section 5, how IPv6 neighbors talk, the Neighbor Discovery Protocol.
Finding the right network is one thing, right? But figuring out the exact hardware address of the server sitting literally right next to you requires a totally different language. In the old days, IPv4 used ARP. ARP basically just blasted these super noisy broadcast messages to everyone in the room yelling, "Hey, who has this IP?" IPv6 completely kills that broadcast noise. Instead, it uses the sleek Neighbor Discovery Protocol, or NDP, which sends targeted multicast messages. It's so much quieter and honestly way more efficient.
But get this, NDP doesn't just find MAC addresses, it actually has absolute superpowers. It automatically configures IP addresses using something called Slack. It hunts down local default routers all on its own without needing a DHCP server. It even performs duplicate address detection, automatically checking to make sure absolutely no one else on the link is using your newly generated IP address. It practically runs the whole neighborhood for you. Which brings us to a pretty fascinating question to wrap things up. We started this explainer talking about manually typing out maps for blind routers, but with the incredible self-configuring nature of IPv6, where devices just find each other, assign their own IPs, and locate their own gateways totally automatically, what does the future of network engineering really look like? If endpoints are getting this incredibly smart, how long until manual routing is just a thing of the past entirely? Definitely something to think about the next time your data instantly crosses the globe.